Hi, my name is Zhou from UCLA, and I'll be introducing our paper, Non-Sequential Graph Script Induction via Multimedia Grounding. First, I'll introduce the motivation behind our work. As humans, we're constantly learning and executing everyday tasks such as making egg fried rice. The same ability is expected of robots and virtual assistants. So, what resources do we have out there to teach us how to perform these tasks? First, there are online textual sources such as WikiHow, which provides a linear sequence of steps to guide us through the task. However, problems may arise during our execution due to empirical circumstances. What if I'm missing one tool or ingredient? Can I skip the corresponding step? What if I mixed up the execution order of two steps? Can I just swap them and move on? These problems are not accounted for by the sequential script. In those cases, we may turn to other instructional resources for information, such as YouTube videos. However, we may run into similar problems, such as where to add a preferred optional step that is not mentioned in the video. So there we have it. While both instructional text and videos are useful resources, neither is able to account for non-sequential step relationships. These non-sequential step relationships, including optional and interchangeable steps, make up an integral part of everyday tasks. Without understanding them, it is unlikely for humans and robots to succeed in task execution. To solve this problem, we propose the task of non-sequential graph script induction, which aims to capture sequential, interchangeable, and optional steps in instructional tasks. This can help humans automate the time-consuming process of learning non-sequential tasks from many sequential resources. It also provides an accurate model of empirical event patterns without having to solely rely on conjectural evidence. For robots and virtual assistants, this can enable global optimization and facilitate multi-agent coordination. It will also teach robots to navigate mistakes and perform on-the-spot improvisation to avoid path-level failures. To tackle the problem of non-sequential graph script induction, we make use of both WikiHow textual scripts and existing instructional video datasets including Crosstask and How to 100 Million. Higher quality labeled videos are used for fine-tuning, while lower quality ASR narrated videos are used for pre-training. Both labeled and unlabeled videos are grounded to WikiHow textual steps through our robust and fault-tolerant grounding mechanism as detailed in our methods section. Inspired by the NetGAN paper, we transformed the graph script learning problem into a path learning problem by treating steps as nodes and temporal relationships as directed edges. The grounded step sequences produced in the previous step are shuffled and concatenated using a special separator token before being passed into the model as examples of valid paths for the given task. Combined with basic cross-entropy loss, we introduce an additional path-level constraint objective via contrastive loss. The negative contrastive samples are generated and fed into the model based on increasing difficulty levels as training progresses. This is designed to gradually teach the model about step selection, local step ordering, and finally global step ordering. After the model is fully trained, we implement step-level constraint decoding to generate a large number of step sequences. Together, they are decomposed into a step adjacency matrix and filtered by a probability threshold. The final results can be easily visualized into a non-sequential probabilistic graph script. Now, let's move on to the experiments section. For automatic evaluation, we constructed the tasks of next step prediction and partial sequence completion. Given a partial step sequence, we ask the model to predict either the immediate next step or all of the remaining steps that lead to successful task completion. Note that here we can have a varying number of correct answers depending on the specific input sample. Ablation study results show that video-to-text grounding, pre-training with unlabeled videos, and the additional path-level constraint together improves performance of the two tasks by 13 to 17% absolute gains compared to existing state-of-the-art textual and visual baselines. For human evaluation, we ask the annotators to evaluate the generated graph scripts based on correctness and expressiveness in terms of each relation type. Annotators have to look at each step in the graph script and determine whether all of its corresponding step relationships are labeled correctly. Human annotation shows our model consistently outperforming the baseline model trained on WikiHow linear scripts by large margins with respect to accuracy and expressiveness. Thank you for listening.